Hello students, welcome to this lecture on work, energy and power, which is given as chapter number 6 of physics for class 11. In this lecture, we will first introduce the subject, then study about notions of work and kinetic energy, the work energy theorem and the work. The terms work, energy and power are frequently used in everyday language. A farmer plowing the field, a construction worker carrying bricks, a student studying for a competitive examination, an artist painting a beautiful landscape, all are said to be working. In physics, however, the word work covers a definite and precise meaning. Somebody who has the capacity to work for 14 to 16 hours a day is said to have a large stamina of work. We admire a long distance runner for her stamina or energy. Energy is thus our capacity to do work. In physics too, the term energy is related to work in this sense. But as said above, the term work itself is defined much more precisely. The word power is used in everyday life with different shades of meaning. In karate or boxing, we talk of powerful punches. These are delivered at a great speed. This shade of meaning is close to the meaning of word power used in physics. We shall find that there is at best a loose correlation between the physical definitions and psychological pictures these terms generate in our minds. The aim of this chapter is to develop an understanding of these three physical quantities. Before we proceed to this task, we need to develop a mathematical prerequisite, namely the scalar product of two vectors. Let us start. We have learned about vectors and their uses in chapter 4. Physical quantities like displacement, velocity, acceleration, force, etc. are vectors. The scalar product or dot product of any two vectors A and B denoted as A dot B is defined as vector A dot vector B is equal to modulus mod of A into mod of B into cos theta, where theta is the angle between two vectors. Please see the diagram, a figure on the right hand side, figure A. Here A is a vector and B is also another vector, and B is the angle between A and B is theta. So therefore vector A dot vector B is equal to modulus of A into modulus of B into cos theta, where theta is the angle between two vectors. Since mod A and mod B and cos theta are scalars, the dot product of mod A and mod B is a scalar quantity. Each vector A and B, that is vector A and vector B, has a direction, but their scalar product does not have a direction. See here, A has a direction, B has a direction, but their scalar product does not have a direction. From equation 1 above, we have A dot B, vector A dot vector B is equal to A into B cos theta. that is equal to B into A cos theta. You see here, you see vector B is a, the product is, here the projection is B cos theta. Projection of vector B is B cos theta. Therefore, A into B cos theta is equal to B into A cos theta. Geometrically, B cos theta, as shown in figure B, is the projection of vector B onto vector A, as shown in figure B. And A cos theta is the projection of A on B, as shown in figure C. This is the geometrical representation shown in the figures. So, vector A dot vector B is the product of magnitude of A and component of B along A. Alternatively, it is the product of magnitude of B and the component of A along B. Scalar projection of A on B is given by the relation vector A dot vector B divided by modulus mod of vector B. The scalar product follows the commutative law. So, this is a property of a vector scalar product. That is, it follows a commutative law. Commutative law says A dot B, vector A dot vector B is equal to vector B dot vector A. Scalar products obey the distributive law. Distributive law says vector A dot sum of vector B plus C is equal to vector A dot B plus vector A dot C. Further, the scalar product, we can find out the scalar product. Vector A into lambda B, that is a multiplier. Lambda is a multiplier. Lambda into B is equal to, we can take lambda outside, lambda into vector A dot vector B, where lambda is a real number. Next, if A and B are two non-zero vectors, then A and B, vector A and B are perpendicular to each other. If and only if vector A dot B equals 0, that is dot product is 0 if the angle between them is 0. For unit vectors I, j and k, I dot j is equal to j dot k equals k dot I, where I, j and k are unit vectors along the x, y and z axis. Therefore, they are perpendicular to each other, so their product is 0. I dot I equals j dot j, that is equal to k dot k, that is equal to 1. Now, we will take up notions of work and kinetic energy and state the work energy theorem. We know from the kinetic equations theory V square minus U square is equal to 2AS, where U and V are the initial and final speeds and S is the distance traveled by the object. So V is the final speed and U is the initial speed. So multiplying both sides by m by 2, that is m is mass by 2, we get m mv square by 2, half mv square minus half mu square is equal to 2 into mas, that is half, 2 and 2 gets cancelled, it becomes mas. So MA, we know that MA is equal to F. Therefore, half mv square minus half mu square is equal to MAS. That is equal to F into S, where the last step follows the Newton's second law of motion. We can generalize this equation as V square minus U square equals 2 into vector A into vector D, where D is the displacement. Both A and D are vectors, please note. So that can be once again written as half mv square minus half mu square is equal to m into A into D. That is multiplying by m by 2, both sides, left hand side and right hand side. We get half mv square minus half mu square is equal to m into A into D. That is equal to F into D. Therefore, half mv square is final kinetic energy. Let it be represented by a letter K suffix m. So half mu square is the initial kinetic energy. Therefore, Kf minus Ki is equal to F vector F into vector D is W. That is the work done. The change in the kinetic energy of a particle is equal to the work done on it by the net force. Thus, we have proved about the change in the kinetic energy, that is Kf minus Ki is equal to W. Let us solve a question on work energy theorem. Find the angle between force F is equal to 3I plus 4J minus 5K unit and displacement D is equal to 5I plus 4J plus 3K unit. Also find the projection of F on D. Answer. So we know from our knowledge F into D, the dot product is given as Fx into dx, that is the component of F along x-axis and component of x along the component of D along the x-axis plus y component of F into D component of y component of D plus z component of F and z component of D. Therefore, applying ratios here 3 into 5 plus 4 into 4 here plus minus 5. Here it is minus 5 into this is 3. That is equal to 16 units. Also we know F into D is equal to Fd cos theta. That is vector F into vector D is equal to Fd cos theta. Therefore, cos theta is equal to Fd divided by mod of F into mod of D here in this equation. That is equal to F into D we have found in this as 16, that is divided by mod of F is 3 square plus 4 square plus minus of 5 square into mod of D is 5 square plus square root of 5 square plus 4 square plus 3 square. Simplifying, we get 16 divided by root 50, square root of 50 into square root of 50. That is equal to 16 by 50 equal to 0.32. Therefore, theta is equal to cos inverse of 0.32. That is the answer. As we have seen earlier, work is related to force and displacement over which it acts. Consider a force F acting on an object of a mass m. The object undergoes a displacement d in the positive x direction as shown in the figure. Please see this object. F is acting on this object at an angle theta, and due to this force the object moves a distance d. The work done by this force is defined as the product of component of force in the direction of displacement and magnitude of this displacement. So the force here is F and its component in the direction of displacement is F cos theta and its magnitude is d. Therefore, work done is equal to F cos theta into d. That is given by vector dot product of vector F dot d, vector d. Therefore, from this equation, we can infer that W equal to 0, that is, no work is done if the displacement is 0, that is, if D is 0 as seen in the example above. Another example of this is a weightlifter holding a mass of 150 kg on his shoulder for 30 seconds does no work on the load during this time. Then the next case is if the force F is 0, no work is done. For example, a block moving on a smooth horizontal table does not do any work because it is not acted upon by the horizontal force. The third case is if the force and displacement are mutually perpendicular, that is, theta is 90 degrees. If the angle between F and D is 90 degrees, the work done is 0. Hence, because theta is equal to pi by 2 radians. Work done can be both positive or negative. If the direction of motion is negative or the direction of force is in the opposite direction, the work becomes negative. The unit of work is joules. The SI unit of the work is joule, which is named after the famous British physicist James Prescott Joule, who lived between 1811 to 1869. There are other alternative units of work or energy. The other alternative unit is erg, ERG, that is the 10 to the power of minus 7 joules. 1 erg is equal to 10 to the power of minus 7 joules. And electron volt is also an unit of energy, which is applied in electronics and the energy possessed by electrons. So that is its value is 1.6 into 10 to the power of minus 19 joules. Calorie is used in heat, calories of heat, and calorie, the energy or a calorie is 4.186 joule. Similarly, in electrical energy, we have kilowatt hours are represented by kWh, kilowatt hour, that is equal to 3.6 into 10 to the power of 6 joules. Let us solve some of the problems on work energy theorem and work. Question number 2. A drop of rain of mass m mass 1 gram, falls from a height of 1 kilometer. It hits the ground with a speed of 50 meters per second. Question A is, what is the work done by the gravitational force? And the next part is, what is the work done by the unknown resistive force? We know that the raindrop falls under the influence of downward gravitational force and the opposing resistive force. The resistive force is proportional to the speed of the drop but is undetermined. Part A. The change in kinetic energy of drop is delta K is equal to half mv square minus 0 because the drop is assumed to be starting from rest. Therefore, that is equal to half into m is gram to be converted into kg. So that is equal to m is 10 to the power of minus 3 kg. V is 50 meters per second. V square is therefore 50 into 50. Therefore, half into 10 to the power of minus 3 into 50 into 50. Simplifying, we get change in kinetic energy is equal to 1.25 joules. Assuming that the drop is initially at rest, that is 0, g is a constant with a value of 10 meters per second square. That is assumed. The work done by gravitational force is given by mgh. Wg is equal to mgh, that is equal to m is equal to 10 to the power of minus 3, g is 10 and height is 1 kilometer. 1 kilometer is 1000 meters, that is 10 to the power of 3 meters. That is equal to 10 joules. Part B. Now here to calculate the work done by the resistive force. We know delta K is equal to Wg plus Wr. That is, the change in energy is delta K is equal to Wg, work done due to gravitational force, plus work done by the resistive force, where Wr is the work done by the resistive force on the raindrop. Thus, Wr is equal to, rearranging, delta K minus Wg. That is equal to delta K, we have calculated above 1.25 joules, minus Wg also we have calculated using formula mgh as 10 joules. Therefore, 1.25 minus 10 is equal to minus 8.75 joules, that is negative. Next example is on work. Question 3. A cyclist comes to a skidding stop in 10 meters. During this process, the force on the cycle due to road is 200 newtons. That is, the force on cycle that is due to friction is 200 newtons. And the distance traveled is 10 meters. Question A is, how much work does the road do on the cycle? Part B is, how much work does the cycle do on the road? Answer. The stopping force and the displacement make an angle 180 degrees. That is, they are exactly opposite to each other. That is pi radians. Therefore, the work done by the road is equal to Wr is equal to F into D into cos theta. That is equal to, force is given as 200 newtons into D is 10 meters into cos of pi. Therefore, that is cos pi is minus 1. Therefore, that is equal to 200 into minus 200 into 10 minus 2000 joules. In this, the negative work that brings the cycle to a halt is in accordance with the work energy theorem. Part B. From Newton's third law, an equal and opposite force acts on the rod due to this cycle. Therefore, it is exactly opposite, means its magnitude is 200 newtons. Therefore, however, the rod undergoes no displacement. Thus, work done by cycle on the rod is 0. Next is section 6.4, that is kinetic energy. The kinetic energy K of an object of mass m which has an velocity vector v is given by the relationship K is equal to half into m, that is mass, into vector v into dot v, that is equal to half mv square. Kinetic energy is a scalar quantity. The kinetic energy of an object is a measure of the work an object can do by virtue of its motion. That is, the kinetic energy is a measure of work due to motion of an object. Let us take an example. Question number 4. In a ballistic demonstration, a police officer fires a bullet of mass 50 grams with a speed of 200 meters per second. So mass is 50 grams, speed is 200 meters per second, and he fires a bullet on a soft wood of thickness 2 centimeters. The bullet emerges with only 10% of its initial kinetic energy. We have to find the emergent speed of the bullet. So, what is the emergent speed of the bullet? Answer. We know that the kinetic energy of a bullet is given by half mv square, that is mv square by 2. So, we know m as 50 gram, it is given. V is given as 200 meters per second divided by 2. Now, this mass m 50 grams is to be converted into kg. Therefore, we use the relation 50 into 10 to the power of minus 3, that is 50 grams converted into kg into 200. V is 200 into 200 divided by 2. That is, the answer is 1000 joules. So kinetic energy of the bullet is 1000 joules. It has a kinetic, as it is also given that it emerges out with 10% of initial kinetic energy. So it has final kinetic energy equal to 0.1, that is 10% of 1000 is 100 joules. Therefore, if Vf is the emergent speed of the bullet and given by the relationship half mvf square is equal to 100 joules. Therefore, we have to find Vf from this relationship. Vf is equal to square root of this 2 into 100 divided by mass m, that is equal to 200 divided by 0.05, that is 0.05 is the grams into 10 to converted into kgs, that is equal to 63.2 meters per second. The speed is reduced by approximately 68%, though kinetic energy is reduced by 10%. That is, the kinetic energy is reduced by 90%. The speed is reduced by only 68%. So, typical kinetic energies of objects. A car weighing 2000 kgs and moving with a speed of 25 meters per second has a kinetic energy of 6.3 into 10 to the power of 5 joules. Similarly, a running athlete weighing 70 kgs and running with a speed of 70 meters per second has an energy, kinetic energy of, possesses a kinetic energy of 3.5 into 10 to the power of 3 joules. A bullet fired with a speed of 200 meters per second and weighing 5 into 10 to the power of minus 2 grams has a kinetic energy of 1000 joules. Falling stone from 10-meter height weighing 1 kg with a speed of 14 meters per second, falling with a speed of 14 meters per second, has a kinetic energy of 10 square joules. Raindrop of mass 3.5 into 10 to the power of minus 5 kg and falling with a speed of 9 meters per second has energy of 1.4 into 10 to the power of minus 3 joules. Air molecule approximately weighing 10 to the power of minus 26 kg and falling with a speed of moving with a speed of 500 meters per second has a energy of approximately 10 to the power of minus 21 joules. The next lecture we will study sections 6.5 onwards. Till then, goodbye.